So for the first lesson of first part of 7.6, we were looking at how we could use derivatives to help us analyze a graph of a function. And so, of course, this would really take place if you had the function but not the graph. And we were trying to use derivatives to help us analyze what was going on at certain points of the graph. So a couple things to note here. For this graph that we're seeing for y equals x squared, if we just look at the portion of the graph from -2 to -1, so from right here, so I'm going from -2 where x is -2 to where x is -1, what is going on with that graph? So as x is increasing, right, x is going from -2 to -1, so it is increasing. What's going on with the y values? So you can see obviously the y values are decreasing. I'm going from 4 to 1, so my y values are decreasing. So that means from that area of the graph, my graph is decreasing. Compare that to this one, from 1 to 2, right? So as x increases from 1 to 2, the y values are also increasing from 1 to 4, which means in this portion of the graph that we would say it is increasing. And you know, the obvious way to look at this is, you know, it's decreasing where the graph is heading downward, and then you hit a 0, and then now we are increasing as the graph is headed upwards. And so just using that idea of increasing and decreasing, we're going to use here in a minute as we look further on. So this one is just asking us a couple specifics that we've already dealt with. So this one's saying, what's the derivative? Well, the derivative of x squared, if I use the power rule, is 2x. So what is the derivative where x is -2? Well, if I plug -2 into my derivative, I get -4. Remember what this tells you though. This is telling you the gradient or the slope at this point. So if you look at the graph at -2, what is the slope? If I were to draw a line on that graph right here, what would the slope of that line be? And that's what you're getting out of this number right here. This would be the slope or the gradient of the line drawn at this point. Same thing for this one. If I said, what is the slope at 2? Well, right here, again, if I were to draw a tangent line right here so that it hits the graph at 2 and then keeps on going, right, we'd say, what is the slope of that tangent line? Well, if I plug in a 2 into my derivative, I get the slope of that line, which is 4. And so you can see that's a positive number simply because this is where the graph is increasing. If I have a negative slope, that would happen where my graph is decreasing, that I see right here. What's happening at 0? So at the point of 0, you can see our slope is 0. If I were to draw a tangent line right here, right, that would be a horizontal line, and horizontal lines have a slope of 0. And so at this point right here where you'd have a horizontal tangent line, you get a 0 slope. And that's what we're seeing with this example right here. So moving on, keep those ideas in mind. We're going to keep talking about those as we move forward. So as I just mentioned up above, to sum up what's being said right here in this box, anytime your derivative is positive, right, that's the area of the graph that would have a positive slope, and so that's where the graph is increasing. If you have a negative slope, that's where the graph is decreasing. We're going to use that concept to help us identify stationary points. Stationary points are points like this one where you have a 0 slope. So this is where the graph is not increasing or decreasing, so we refer to this as a stationary point. And so anytime you get a stationary point, that simply means the derivative equals 0 at that point, or you would say we have a 0 slope. The graph is not increasing nor decreasing at that point. For those points, it could either be a maximum or a minimum. So if you look at this point right here, we would refer to this stationary point as a maximum because it's at the peak of a graph. We would refer to this stationary point as a minimum since it's at the bottom point of a graph. But both a minimum and a maximum are stationary points. And so both cases, whether it's a min or a max, both of those would have slopes of 0. And so that's kind of what this part is talking about right here. Here's just some vocab that you should be familiar with. So relative extrema or local extrema are just stationary points. So, and those are maxes or mins. Automatically, as soon as you see the word max or min, you have to connect that to this, which means at that point, my derivative equals 0. And so that's the key concept you got to make sure you take away from this. Anytime you have a max or a min, your derivative equals 0. So if we were to just take any function without looking at the graph, if I were to just look at a function and I was trying to determine what my stationary points were and if they were a maximum or a minimum, how would we do that? And so that's what's going on here with a first derivative test. So just a side note that you see on this. How would I know, just by looking at numbers and not a graph, how would I know that this is a maximum? Well, look what's occurring on the left side of this point. To the left of this stationary point, you can see that my graph is increasing. So my graph is increasing, then all of a sudden it hits 0, and now it's decreasing. So anytime you go from increasing to decreasing, that would always occur at a maximum. If you compare that one to this one here, right, at this stationary point, we're going from decreasing to increasing. So anytime you change from decreasing to increasing, that would happen at a minimum point. And so what we can do on this is we can test the derivative on either side of our stationary point to determine what kind of a stationary point that we have. So if you look at the table that you see here, and in a nutshell, this is what I was just describing with the graph for when you would have a maximum or a minimum. So here's a good example because this has several stationary points in it. So remember, all this is taking place without looking at a graph. So I need to not only identify where my stationary points are, but then I also need to classify them. So in this case, we got to start out by just taking the derivative of the original function. So that's what you're seeing right here. So we found the first derivative. And remember, anytime you have a stationary point, that's where your derivative equals 0. So if I set this entire function equal to 0, and that's what you're seeing right here, if we solve by factoring, these are the solutions I get. 0, -1, and +2, which means these are the locations where I have relative extrema, because we found those x's by setting our derivative equal to 0, which means these are the points where I'd have a 0 slope. So at this guy, this guy, and this guy, we have 0 slopes. So if I were to plug in 0, -1, and 2 into the original function, then I could get y coordinates to go with them. And that's what you're seeing in this line. So if I took 0 and plugged it into the original function, I get 3. So this is one ordered pair. If I plug -1 into the original function, I get this. So that's another ordered pair. And then if I plugged in +2, I get this. So at those 3 points, we have some type of relative extrema. So the extra step would be then to figure out what type of extrema they are. Are they a max or a min? And to do that, we're going to use some numbers on either side of that point to see what's going on with the slope. Is it increasing or decreasing? So if I take a number to the left of -1, like -2, and if I plug this into the derivative, I'm going to come out with a negative slope. So on the left side of this point, my graph is decreasing. To the right of that point, so now I'm going to plug in a point to the right of that. I can't use 0 because I already know what's going on at that point. I need something in between that. So the next point to the right of -1, before I get to the next stationary point, could be a number like -0.5. If I plug this into the derivative, I get a positive slope. So surrounding this stationary point, my graph is going from decreasing to increasing. So that tells me when I have a graph going from decreasing to increasing, that must be at a minimum point. So that's how I would classify this ordered pair as a minimum point. If I go to the next stationary point, so 0, 3 was my next stationary point, and we're going to test numbers on either side of him to see what's going on with our graph. If we plugged in -0.5 into the derivative, I can see that my graph is increasing to the left of 0. And if I plug in 1 into the derivative, I can see that my graph is decreasing to the right of 0. So we are going from increasing to decreasing, which means if I go from increasing to decreasing, that would occur at a maximum point. And so I could now classify this as a max. Again, you could do that one more time for this ordered pair. plug in a number to the left and to the right of him into the derivative, and you can see that you're going from decreasing to increasing, which again occurs at a minimum point. And so that's the way that we would classify our stationary points. So here are the 3 stationary points along with their classifications that we just found with the first derivative test. Of course, if you had a graph to look at, so if you were to put this into your graphing calculator and graph it, this is what you would see, and pretty easily I can identify this is a minimum, this is a maximum, and this is a minimum. So if I have the graph to look at, I wouldn't have to go through all this. But there's going to be cases where you're asked to show with the first derivative test, how do you prove that this is a minimum or if this is a maximum? And this is how we would prove it with the first derivative test. And not just saying, well, I'm looking at the graph like we are on this one right now. So that's how we'd prove it. Here's the last thing to end on with this one. You're going to be asked to show with inequalities where your graph is increasing and where your graph is decreasing. So that's going to happen around these stationary points. So I'm going to use -1, 0, and 2 to show where the graph is decreasing and where it's increasing. If I use the farthest one to the left at -1, so right here you had the minimum point, the first stationary point, which occurred at -1. Well, you can see that to the left of it, so from -infinity all the way up to -1, my graph was decreasing. And then from -1 to 2, or sorry, from x is -1 to where x is 0, my graph is increasing. And from 0 to 2, my graph is decreasing. And then from 2 to infinity, my graph is increasing. And so that's what you're seeing over here on the right side. Now you could do this with inequalities. You don't have to use this kind of interval notation. Either way is fine. You could do it with an inequality, you could do it with interval notation. As long as you do the proper notation, it doesn't matter. One last side note, if I'm going to do something like this, or if I'm going to use inequalities, keep in mind that at your stationary point, your slope is 0. So if I'm going to talk about the interval from -1 to 0 as it is increasing, I would not include -1 and 0 as part of that. It's in between them that the graph is increasing. So if you were going to do this with an inequality, for this part right here, we would make sure that we say something like the graph is increasing where x is greater than -1 but less than 0. Right? I would not use greater than or equal to. I would just use the less than and greater than signs, because we're not including those points, because it's not increasing at the point but only in between them. And so I just, little notation, things like that, you got to be careful of when you do things like this. So that's why in these points they use the parenthesis and not the hard bracket. So the hard bracket would have told me that I'm including -1. The soft parenthesis tells me that it's not inclusive.